This is an autonomous robot I built. It's designed to be a companion capable of navigating its environment and building up context and intuition while doing so, all powered by OpenClaw. The robot is firstly capable of point-to-point navigation, which allows it to traverse any environment fully autonomously. The motor controller, CAD, and navigation setup are all fully custom. You can see the robot effortlessly going through its environment in the path planner in the bottom right. The Nav2 library uses a pre-scan map of the environment to find an optimal path for your robot, considering global optimality and also local behaviors such as speed and path adherence. It does this by merging an obstacle layer resulting from the robot's LiDAR scans with a pre-scanned static layer and inflating a danger zone around any obstacles. This enables very robust and impressive navigation, such as this other autonomous robot I worked on for my collegiate robotics team I was a captain of. Back to my demo, the robot can also dynamically avoid obstacles picked up by its LiDAR scan, which is crucial for safe operation in changing environments. You can see the Nav2 planner updates its trajectory when the obstacle is seen and replans movement when there's an available path. This still requires a human to tell the robot where to go, so the real question is, how can the robot automatically process and move around its environment as a living agent? One idea is to pass the robot's camera feed into a large language model which will process the environment visually and output navigation commands back to the robot. But the issue is that LLMs are stateless, meaning you can tell it something and then in the very next chat it will have forgotten. This is bad if we want the robot to build up knowledge and recall things. My solution is to pass a camera feed into a vision language model first, which will output a list of seen objects and observations about the robot's environment. These thoughts get stored into a short-term memory, and every n frames, an LLM is asked to distill the current short-term memory bank into a single long-term memory entry. The user may then ask a question or command, resulting in the VLM outputting a navigation command using its memory bank as context. When deployed, the pipeline will look something like this, where the robot sees from its camera and iteratively thinks while referencing its memory banks as context. For example, here's one thought, which is a list of objects and environmental observations. The short-term memory is then a collection of these thoughts, and the long-term memory is a distilled list of seen objects. This enables what I call semantic recall, where we ask the robot to navigate back to a specific location it had seen prior. Notably, this location was not pre-named. Rather, it was remembered and classified by the VLM itself. The robot will begin navigation back to the point fully autonomously. The robot may also do object recall, such as asking it where it last saw a backpack and going to navigate there. The short-term and long-term memory approach allows the robot to both process its environment and become a cognitive part of it. If robots and AI are going to be a part of our lives, we must build systems that allow them to truly inhabit and navigate our world. We are moving past machines that simply navigate through our world and moving on to agents that actually understand it.